In section 4.5, we look at some of the characteristics of molecules. So it's important to realize that molecules are covalent compounds, and they form discrete units of atoms that have a characteristic mass and a characteristic 3D shape. So the molecular mass, sometimes called the molecular weight, is simply the sum of all of the masses of the atoms that are present in a molecule. So if I wanted to calculate the molecular mass of methane, what I would do would be to find the mass of carbon and hydrogen in the periodic table, and then I would recognize that the mass of one whole methane molecule is the mass of one carbon atom plus the mass of 4 hydrogen atoms. So I'd add all of those numbers together, and that would give me the mass of one molecule. So here's a few examples from the book. So in A, we need the mass of carbon and the mass of hydrogen. And then we're going to do 2 carbons plus 2 hydrogens. Add those guys together, and that'll give us our mass of one C2H2 molecule in AMU. 26.0 036 AMU. And the same for the others. For B, we need the mass of one carbon and the mass of one oxygen. So one carbon is 12.01 and one oxygen is exactly 16. So that will be 28.01 AMU. We can do C. We have one carbon, but then 2 oxygens. And so that will give us a mass of 44.01 AMU. And finally, D, we have one boron, and then we have 3 fluorines, and the mass of that molecule 67.81 AMU. So it's a pretty simple concept. You just add together the masses of the atoms. So as we mentioned previously, ionic compounds exist in 3D crystal lattices, and these crystal lattices are very large and contain billions upon billions of ions. However, molecular compounds exist as discrete 3D molecules that have their own shape. And normally there's just a few atoms in our molecules, perhaps less than a dozen. So a question that comes to mind is, what are the shapes of these molecules and what determines the shape of them? And the theory that we're going to use to determine the shape of molecules is called valence shell electron pair repulsion theory, and most people just call that VS-EPR theory because it's a bit of a mouthful. And the idea is pretty simple. It says that electrons repel each other and thus want to be as far away from each other as possible. So keep in mind that a bond between 2 atoms is simply a pair of electrons. So what VS-EPR theory is saying is that we want to try and keep each bond as far away as possible from each other bond in order to minimize repulsion between these electrons. So I'll give you a few examples. In the molecule BeCl, we have only 2 atoms joined together, or we have, only 3 atoms joined together by 2 bonds. Those 2 bonds attempt to keep as far away from each other as possible, and the best way to keep 2 things out of each other's way is to have them at 180 degrees. So the 2 bonds in BeCl2 are at 180 degrees to each other. In methane, where we have 4 bonds, we find that the best way to keep 4 bonds out of each other's way is to have an angle of 109 degrees between them. And so you can see that as the number of atoms attached to our central atom gets larger, things start getting more crowded and the bond angle reduces as a result. So there are 3 shapes that we would like you guys to know. The linear shape, which we're going to observe when we have 2 bonds to a central atom. The trigonal planar shape, which we're going to observe when we have 3 bonds to our central atom. And the tetrahedral shape that we're going to observe when we have 4 things attached to our central atom. Now, it's important to recognize that in addition to knowing the names of these shapes, we do expect that you also know the bond angles. So let's look at some trigonal planar molecules. Both of these molecules here are trigonal planar because we have 1, 2, 3 things attached to the central atom in each case. As a result of that, the bond angle will be 120 degrees or thereabouts in each case. Now, there's something to be mindful of. It's not always just an atom that is attached to the central atom. Sometimes it's a lone pair. And when we do have lone pairs, what will happen is the bond angle can get a little distorted. Sometimes that's actually incorrect there. So all of these molecules here have 1, 2, 3, 4 things attached to them. 1, 2, 3, 4. 1, 2, 3, and 4. So they're going to have bond angles that are near 109 degrees. But what we see is that adding the lone pair, it's a little bit more repulsive than just a bond to an atom, and it causes the bond angle to get decreased a little. So in methane, where we just have atoms attached to our central atom, the bond angle is exactly 109 degrees. In ammonia, where we have 3 atoms but 1 lone pair, it's a little less than 109 degrees. And in water, where we have 2 attached atoms and 2 lone pairs, it is a lot less than 109 degrees. And that's a general trend, that adding lone pairs to our central atom causes the bond angle to get squished up a little bit. Okay, so this is the information that you guys need to remember. To determine the molecular geometry, what you're going to do is draw the Lewis structure. And then you're going to count the number of things, atoms and lone pairs, that are attached around the central atom. This will be either 2, 3, or 4. This will give rise to one of 5 different geometries. If we have 2 things attached to our central atom, none of them are lone pairs, we will have a linear molecule with a bond angle of 180 degrees. If we have 3 things attached to our central atom and none of them are lone pairs, we will have a trigonal planar molecule and the bond angle will be 120 degrees. If, however, one of those 3 things, that's attached to our central atom is a lone pair, then we don't call the molecule trigonal planar. We say that it is either bent or angular. You can take your pick there. And the bond angle will be a little less than 120 degrees. If we have 4 things attached to our central atom and all 4 of them are atoms and we have no lone pairs, we will have a tetrahedral molecule and the bond angle will be 109 degrees. If one of our 4 things is a lone pair, the bond angle gets squished up a little bit and it'll be a little less than 109 degrees, and the molecule is described as having the trigonal pyramid shape. If 2 of our 4 things are lone pairs, the bond angle gets squashed up even more and it will be a lot less than 109, and we can describe the molecule as being either bent or angular. So you need to know the information in this table, which means that you need to know the names of each of these 5 types of molecules, and we also need to know the bond angles. So this question asks, what is the geometry of the ammonium ion? And the first thing that we're going to need to do is to draw a Lewis structure. So there is nitrogen there, and there is hydrogen over here. So we have 1 nitrogen, and nitrogen's in group 5a, so that gives me 5 valence electrons. And then we have 4 hydrogens, and they're each in group 1a. So in total, we have to do one thing, and then we have to take 1 electron away because this guy's got a positive charge. So in total, we end up with 8 electrons. Now, as hydrogen is always an outer atom, we know that nitrogen must go in the middle. So our Lewis structure that we're going to start with is this. And that's actually our final Lewis structure, because making the 4 bonds to hydrogen consumes all of my 8 electrons. I have no electrons after making those bonds. My nitrogen has an octet and my hydrogen has a duet. So now I have to add up the number of things that are attached to my central atom. So I have 4 attached atoms, and I have 0 lone pairs. So consulting my table tells me that this is the tetrahedral geometry, and the bond angle will be exactly 109 degrees. Now, we already mentioned that we can tell whether a molecule is polar or not by considering the things that are attached to the central atom. And we said that polar molecules always have more than one type of thing attached to the central atom. So in the case of a water molecule, we have hydrogens attached to the central atom, but we also have lone pairs, so that's why we classify this guy as being polar. However, in the case of methane, everything attached to the central atom is exactly the same, and so we classify methane as being non-polar. Another way of recognizing whether a molecule is polar or not is to consider whether the dipoles of each bond cancel out. So for example, in CO2, we know that each bond is polar, and because carbon has a smaller electronegativity than oxygen, that tells us that the electrons are being pulled towards the oxygen ends of the molecules. So you can see here that we've got 1 dipole pointing to the left and 1 dipole pointing to the right. So overall, it has no dipole, and carbon dioxide is a non-polar molecule. Now, if we look at a water molecule, according to VSEPR theory, has a bent geometry. The bond angle in here is going to be considerably less than 109 degrees. It turns out that it's about 104.5 degrees. Now we know that hydrogen is less electronegative than oxygen, so electrons get pulled towards the oxygen end of each of those bonds. And what we can see is we have 1 arrow pointing up and to the right, and 1 arrow pointing up and to the left. So overall, the left and right bits are going to cancel out, and there is a net molecular dipole that points upwards. And that kind of agrees with what we said, that the oxygen end is negative and the hydrogen end is positive in a water molecule. So the shape can help us visualize how the electrons are being pulled around in space. Let's look at a few molecules where we have three things attached to the central atom. I'm just going to put this lone pair here on this ammonia molecule. So BF3 has the trigonal planar geometry. It's flat and there's a bond angle in here of 120 degrees. Now you can see that the boron is less electronegative than fluorine, so electrons are being pulled towards the fluorine in each case. So this molecule is nonpolar because we have electrons being pulled to the left and down. We have electrons being pulled to the right and down. So that means that those two add together, the left and right bits cancel out, and we just have a net pull downwards. Now that is countered though, because the fluorine at the top here is pulling upwards. So overall, all of the bond dipoles cancel. In the case of ammonia, because we have one lone pair and three attached atoms, we have the trigonal pyramid geometry. Hydrogen is less electronegative than nitrogen, so in each bond the electrons are being pulled towards the nitrogen. And so we can hopefully see that overall, while the left and right components do cancel out, the upwards components don't. And that means that this is a polar molecule where the nitrogen end will be negative and the hydrogen end will be positive. So here's an example where we have two molecules both with tetrahedral geometry, so 4 attached atoms, but and no lone pairs. This molecule is nonpolar. We have 2 bonds that are pulling electrons down and to the left, and down to the left and to the right. And then we have 1 bond that is pulling down. So when we add all of this together, we just have a net pull downwards, but that's cancelled by the net pull upwards. So all of the dipoles cancel out. Now in the case of this molecule over here, CH3Cl, everything is getting sucked upwards towards the chlorine, and so that one has a dipole where the chlorine end of the molecule is negative and the hydrogen base of the molecule is positive. So by considering the shapes of these things, we can decide whether our molecule is polar or non-polar and whether the dipoles cancel out or not. Now it takes a little bit of practice, but the shape, in addition to paying attention as to whether we have more than one thing attached to our central atom, can really help us decide if a molecule is polar or not. And so you can see all of these molecules where I've drawn in the blue arrow here, they are all polar. And all of the ones where I haven't, the dipoles cancel out. So something that you should be able to do is to decide if a molecule is polar or non-polar, and also to assign a molecular geometry to a molecule if you're able to draw its Lewis diagram. So we're going to do both of those things in this one problem here. So we're going to need to begin with a Lewis diagram. So we've got carbon and bromine in our first one. So carbon's in group 4A, so that gives me 4 valence electrons. And then I have 4 bromines, and they're in group 7A. So that means we've got a total of 28, 32 electrons. So carbon's going to go in the middle because it's group 4A, and then bromine is going to go on the outside because it's group 7A. So getting our basic structure, each of these bonds uses up 2 electrons, uses up 8 electrons, and that gives 24 electrons remaining. Now I'm going to finish off the lone pairs or the octets on my bromines, and that's going to take all of my remaining 24 electrons. So now we're down to 0 electrons, we're ready to roll. Okay, so what we have here is 4 attached atoms. We have 0 lone pairs. So this particular geometry is tetrahedral. Now I have to decide if it's polar or not. As there's only one kind of thing attached to the central atom, I'm going to say that that is non-polar. Okay. Now we can do the same for a boron trichloride. So boron is in group 3A, so 3 valence electrons, and then chlorine is in group 7A. We have 3 of those, so that gives me 7 valence electrons apiece. So 3 plus 21, we have 24 electrons. As boron is in group 3A and chlorine is in 7A, boron goes in the middle and the chlorines, go on the outside. What this means is once we finish off our lone pairs, we use up all of our electrons. We use 2, 4, 6 electrons to make the bonds. That gives 18 electrons. And then we put 6 electrons on each of the 3 chlorines. That uses up all of our electrons. So when I look at this structure here, I have 3 attached atoms. I have 0 lone pairs, and if I consult my VSEPR table, that tells me that this molecule is trigonal planar. Now you probably want to print out a copy of a VSEPR table. As everything that is attached to the boron is the same, this molecule is non-polar. Okay. Cool. So let's just kind of look at the comparison of some of the properties of molecular compounds versus ionic compounds. So the types of elements that are present in ionic compounds are metals bonded to non-metals, whereas in molecular compounds, we're looking at bonds between non-metals only. The bonding that takes place in ionic compounds is a result of the transfer of electrons between metal and non-metal atoms, whereas the bonding that takes place in molecular compounds is a result of the sharing of pairs of electrons between atoms. The fundamental unit of an ionic compound is called the formula unit, whereas the fundamental unit of a molecular compound is the molecule. At room temperature, all ionic compounds are solids. They have very high melting points, whereas molecular compounds can be either gas, liquids, or solids. The water solubility of ionic compounds is usually very high, although there are some that don't dissolve well. But we have a great deal of variability with respect to the water solubility of molecular compounds. A lot of that is dependent on whether the molecules are polar or not and how strongly they interact with water molecules. The melting and boiling temperatures of ionic compounds are usually very, very high, whereas the melting and boiling points of molecular compounds are normally pretty low. The electrical conductivity of ionic compounds is good as long as the substance is either melted or in solution, so the ions can move around, whereas the electrical conductivity of molecular compounds is normally very low. Okay, so that concludes chapter 4. I hope you found the videos helpful.